Hey, good afternoon. Today I'll go discuss chapter 9, decision theory, decision analysis, and I have also a bit of more examples than in the book. Here the most important part in the book is just the 9.1, and then most of the rest of the book is examples, although these examples are this multi-stage decision analysis, hierarchical decision analysis, and also a bit of discussion then personal versus institutional decision analysis, and I will also then discuss some things which are not mentioned in the book but related to difficulties in kind of the decision analysis, selecting utilities or cost functions. During the second part of the lecture, I will also discuss a little bit about the project presentation, some advice for that. First, the terminology. So, we want to make some decisions, sometimes they are also called actions, and these decisions or actions could be also just that what we report as a prediction. Even in a way that the posterior distribution is that what contains all the information, the updated information. So we had some prior information, and then we have a model, and we combine these with data, and we get the posterior distribution and predictive distributions describing our uncertainties. But even then, we might make then decision or action that we report the whole posterior, or we report some summaries, and which summaries then we should report in different cases. Potential consequences. After we've made some action, that action itself can affect then what are the possible consequences. If we are just making a prediction, it doesn't necessarily change what is the consequence. If we predict weather, predicting weather doesn't change what kind of weather it's going to be next day. But if we predict that the patient would need surgery and we do the action of surgery, then that could affect also what are the possible consequences after that. These consequences X, they can be categorical, ordinal, real, scalar, vector, multivalued, something quite complex. And then we assume that there are different consequences that could happen, and we have the uncertainty that which of them happen, and we have the probability distribution of consequences, and these can then depend on decision or action. In case of weather, predicting next day weather, the probability would be the same despite what we predict. But if we decide to make a surgery or not, we would have a different probability distribution. Or at least it would be useful to have a then different probability distribution for consequences depending what is our decision. And we would like to have then these good models for predicting what is the probability distribution of consequences given some decision. Notice that now in decision making, these decisions are controlled, so there is no probability distribution for D, except instead we are saying that, okay, we can choose any of these actions or decisions. And then, in order to use the mathematical framework, we need to map consequences to real values. So this could be then money, as in euros, or in medical cases, when we decide to whether to make a surgery or not, expected lifetime, given that decision. And then this utility function can map these more complex consequences to some real value. I usually talk about utility functions, but then they can be also cost functions or loss functions. And then we can compute expected utility. So knowing what would be the utility or cost of certain consequence, and since we have the probability distribution describing the uncertainty, we can then compute what would be the expected utility. What would be expected lifetime for a patient, and then we would compute separately expected lifetime given surgery or no surgery. And then we could then choose a decision which maximizes the expected utility. So we would like to maximize the expected lifetime, or we would like to maximize amount of money we get. I'll start with a very simple example, just two possible choices. Helen is going to pick mushrooms in a forest. She wants to make some mushroom dish, likes mushrooms. She notices a paw print which could be made by a dog or a wolf. Helen measures the length of paw print and then Googles how big paws dogs and wolves have, and then tries to infer which animal has made a paw print. These curves are not actual distribution of length of paw for wolves and big dogs. They are just toy curves, just some Gaussians, but kind of illustrating that we could have this kind of distribution that actually small wolves could have similar paw print size as big dog. But we can also see that if the paw print is really big, it's more likely that it's wolf's paw print. And then Helen computes likelihood of wolf is 0.92. So just based on that observation, it's more likely. But then there are more big dogs around us, and she assumes then that in her living area there are about 100 times more free-running dogs than wolves, and so gets this prior probability for wolf being just 1%. And then she can then compute the posterior probability that it's a wolf or dog. And now, taking into account the prior information, it's more likely than a posterior that it would be dog. The posterior probability of wolf just 10%. And now, so she went back home to consider what to do, and now she wants to make a decision whether to go back to the forest and pick mushrooms, so she could get this mushroom dish. So if she doesn't go to pick mushrooms, utility is 0. It doesn't matter whether there's dog or wolf, still no mushrooms. Helen assigns positive utility 1 for getting fresh mushrooms. But then there's additional, so there's a negative utility minus 1000, that she goes to the forest and wolf attacks. Or she might be just even that she just doesn't like even seeing wolf, kind of getting scared even if the wolf would not attack. But anyway, so minus 1000 for possibility of encountering wolf. So we can then make this table of these decisions, and then what are the consequences. So if a decision is to stay home, the consequence is no mushrooms and no mushrooms. It doesn't matter whether it is wolf or dog. If the decision is go to forest, then if its animal is wolf, she gets scared, runs away, minus 1000. And if it's a dog, she gets mushrooms and can get these delicious mushroom dish. And this kind of the same way in more complex, we can make these tables, or for a continuous case, of course, then we would have kind of infinite table, but the similar idea. And then we can compute the expected utilities when we add probabilities. In stay home case, because the utility is 0, it doesn't matter what are the probabilities, the expected utility is 0. And going to forest, we had a 10% probability for minus 1000 utility, so that part is minus 100. And then we had a 90% probability for utility 1, so we get there 0.9. And then we have the combined utility. So different conclusions on what decision to make. Maximum likelihood decision would be to assume that there is a wolf. Maximum posterior decision would be assume that there's a dog. But then, if takes into account also the utilities, then Helen decides to stay home. It is more likely that the animal is dog, but there's small probability for this big cost. And this also illustrates that we need to carry uncertainties related to these all consequences until final decision making. So if there's a small probability of very bad events, we need to take into account also those very small probabilities. And this is typical also for human decision making, that humans actually very often do things kind of avoid very small probability events just because kind of assuming that the cost is bad. Humans are just quite bad also estimating these probabilities, and then at least in some cases we can get some benefit from using math statistics help. I'll come back to bit of these different problems with these, specifically how humans are bad in with the utilities and cost functions. So the example with several choices. So Andrew Gelman used to have. So this is in one of his books, and he did it at least a couple times in a class. So that he had a glass jar, and then he had collected with help from his son a lot of quarters, and then for the kind of that not deciding himself or knowing how many coins there are going to be, made it so that make a line to the side of the jar and then just fill with the coins, but not counting how many coins there are until then the level of the coins were at the line. And then he asked someone else to count at how many coins there are, mark that on a piece of paper, put it in an envelope, and then put the coins back to the glass jar. So he didn't know and couldn't kind of reveal by his behavior. When he then asked students that, okay, let's estimate that the students can guess how many coins there are. So it started by first discussing that, okay, how to make estimates so that the students could discuss what would be likely value and what would be the uncertainty in which range the number of coins might be. And then I just don't have the patience to then do this with you. So what they usually ended up was something that 150 coins was kind of the most likely, and then somewhere between 100 and 150 coins was the kind of the what class together agreed, and some kind of Gaussian approximation to uncertainty. Now, of course, the number of coins is not actually Gaussian, so it is discrete, so there would be, for each specific number of coins, there's a bar, there's a probability, and you can think then that this would be the, as we had a table of actions or decisions and consequences, so this could be also then think that you have, for each number of coins, you have that column in a table. And now I give you already then the kind of the description of uncertainty about the amount of coins, but now I also ask you then that what would be your guess for the number of the coins, and if you guess correctly, you would get all the coins in a jar. Okay, someone?
Is the mean anchored?
So it happens now that this is symmetric distribution, and mean and mode is at 150.
But is the mean conditional on the first, like?
So the mean is conditional on what the students estimated when they saw.
Because if that was a number said first, then the whole distribution will be conditioned on that number due to second.
No. So the students had long discussion about the number of coins. We don't know what all the values they mentioned during the discussion, but in the end they agreed that, okay, this is what they assumed, that what is their uncertainty about the number of coins. And given that uncertainty, what would be your decision? You get all the coins if you guess the number of coins correctly. No guesses?
125.
Is it 125? 150? Okay, there's a couple alternative choices that what it could be. So 150 is the most likely value. So then you would be most likely to win something. But then there could be also the possibility that, so I have a €2 coin here, and now I have it in this hand or not, and now I ask that if you guess correctly, how many coins I have here, you can get all of them. What would you need? What would be the best decision then?
To guess one.
Not to guess, because you can have or you can not have, and I can guess or I can't guess. So
Yeah, but now it was that if you guess correctly, you get all the coins. So if you guess the number of coins correctly, you get the coins.
In your hand or?
In my hand. So I have here 0 or 1.
Positive infinity.
No. So your choices are 0 or 1, so you should guess 1, because if it's 0, you won't win anything.
Yes. So same here, that yes, this would be the most likely thing to say, but if we take into account the possible utility, that if you would have a linear utility for money, then if we add here the linear utility, and again it would be not continuous, but we would have for all discrete number of coins, we would have utility. And then if we multiply the probability and utility, to maximize the expected utility, you would actually guess something bit larger than 150. But now this depends on then your utility. Is your utility here the linear in number of coins? Because some students might just get the enjoyment of winning the bet no matter what the reward is. And then it would be the most likely value that they should guess. And of course then, when we go from, so this was also discrete because number of coins is discrete. But if we go to other examples, we could have also continuous distributions for uncertainty and continuous utility functions.
But if you would guess if you would do this over the lifetime, then you should always guess the mean, because.
So again, if you do this over a lifetime, so if you would have that in every class you take, the lecturer would offer you this bet. If you are just interested in getting the money away, you would always guess the most likely value. But if you are interested in over time to get as much money as possible, you would guess something which is a bit higher than the most likely value. Just because guessing a bit higher value, even if it's less likely, there's a higher utility if you guess correctly. And this is kind of the one problem in human decision making, that some of the decisions humans make are kind of rare. Like if you would be thinking that you're buying a house, some may think about the expected utility of buying a house many, many times, but some might also think that they will buy 1 to 3 houses in whole lifetime. So it might affect that also what to do. Actual utility functions are rarely linear. If you think about the money thing, if there would be a bet for you where you could win, or maybe some task for you that where you could get 100 euros, what is the utility of 100 euros for you, and what it would be for Bill Gates? So, and at the same time, if you are completely broke, again, even few euros might be worth some task. So it is well known that the money, it's not linear. There's also these kind of examples that the betting examples. So you have 50% chance of winning 1 million and €5, and 50% of chance losing 1 million euros. Expected utility is €5. So if you are going to do this repeatedly, you would of course choose this. Every time you have probability of getting €5, expected utility is 2.5 euros. And then given 1,000 times, you would have won then 2,500 euros. But it's quite likely that you would not want to take this bet, because if you happen to lose, it would be quite annoying for the rest of your life, kind of how it would affect your quality of life, having 1 million debt at this moment. So these are really linear, and kind of need to take into account that here there's additional consequences of these choices.
But the losses are more like this utility than the gains. It's not like -1 times the...
Yeah, so there's additional consequences. Of course, if you would have already billion euros, then you probably could take this in a way that if there's not much cost of making these bets, then you could do it and then keep winning money. So it's not linear, it depends on your wealth already. What is the cost of human life? When we have these medical decisions, whether to make a surgery or not, or kind of what kind of safety equipment you have in your car, whether you go skydiving, in all of these kind of, we could think that, okay, you put some price for your own life, and then there's some small probability, and from there we could then, actually from the small probability, we could also kind of backtrack what is the kind of your estimate for your value of your life. But then people don't usually make this kind of the monetary connection. In society, in a way, if we think that, like in Finland, we would like to, how much money is put to different policies to reduce premature deaths, then at the kind of the institutional level, it's more reasonable to consider these, but then it's still very difficult. And it's something that I've seen one paper discussing this kind of decision of surgery or not. So patient comes in the hospital, what tests are made to the patient, how they affect how well we can predict whether there needs to be surgery or not, and then what are the losses and utilities. And in only one example where they had assessed cost of human life. The book has the example of radon, and at the institutional level discussing that, okay, how much money should be put in repairing houses that there would be less radon gas inside the house to reduce the number of premature deaths. But these are rare cases that go into thinking about the having euros. And of course, it gets more difficult if we think that how costly treatments we should have for very old people who are going to have short amount of lifetime remaining, and how costly treatments we should have for children, which would have then much more life years ahead. And multiple parties can have different utilities. Then it's complicated. How do we agree on how to combine these? And of course, there is cost of human life, multiple parties having different utilities. Then it's politics. It is possible to use these models to make predictions on what is going to happen depending on different decisions, and it's possible to give guidance also that if the utilities and costs would be like this, then what would be the expected utilities or costs. But it's likely that in many cases it is then politics to then agree on what to do. For companies, this is usually easier. Many companies can actually have the utility as a money, how much money then they can get from customers. And then it can be much easier to optimize it. And it's kind of when the company is big enough, having a lot of customers, how to optimize these decisions. We may have also these decisions in multi-states, and so section 9.3 has this example. A 95-year-old has a tumor that is malignant with 90% probability. Based on statistics, expected lifetime is 34.8 months if no cancer, 16.7 months if cancer and radiation therapy is used, and 20 months if cancer and surgery. But then there's a probability of dying in surgery. For 95-year-old, it's higher likelihood that in surgery getting, for example, some bacteria, and then dying because of this drug-resistant, antibiotic-resistant bacteria taking over. And of course, just otherwise, kind of the surgery might be too much for the body. And then expected lifetime 5.6 months if there's a cancer and no treatment. So the one now we can see the different consequences depending on actions. And then which treatment to choose. Here we can have quality adjusted lifetime, so that these were just first the lifetimes, but we do the quality adjustment so that we subtract 1 month for the time spent in treatments. And then we have the first, there was the probability that there's a tumor with 90% probability, and then we can have this quality adjusted lifetime. So, so there's the 90% probability that there's a cancer, and if we use radiotherapy, we have the certain months, or no cancer, but since we are giving the radiotherapy, we are then subtracting -1, and so we get the expected utility for radiotherapy. Surgery, bit more complicated because it has also then probability of dying. So there was 35% probability of dying, and then we get the 0 lifetime, and 65%, which included again then the probabilities for having cancer or not, and then -1 for the time spent in treatments. And no treatment, again, there's some probability that there's no cancer. And then we can even go further, that what if we would have additional tests which could change this probability, so we could have a more accurate information whether there's a cancer, but also that additional test could be biopsy. So again, taking a kind of the small intervention for the body, which could have also then the possibility of getting the condition worse. And what would be the cases where kind of combining information from different tests. This design of experiments is currently the most common example of where this decision analysis is used. Which experiment would give most additional information? In your exercise this week, you have that kind of example also, that what decision to make. You can also think about this bias as an example, that what if it would be so that there would be too much uncertainty and we could not yet know whether this is category 2 or category 3 hazardous chemical, and then the company would like to sell it, and they would prefer to sell it as a category 2, and then they would like to make additional experiments to get uncertainty smaller to check that whether it is in category 2. And then which dose should be used in the next experiment to reduce the variance of LD50 as much as possible. And this way less experiments need to be made. These kind of experiments are used in drug testing. This been used it was quite many years ago already. FDA in US approved this kind of drug testing, that when the patient comes in, the doctor connects to the system which, based on the previous results, suggests the dosage for this patient. And then when the patient uses the drug, so the problem is that it's common with the drugs that, so if this is the dose, it's common that start with a very small dosage, because then it's less likely to have side effects. But with small dosage, there's also a problem that there's no effect. The old way, and this is still something that is way too common, is to start with very small dosage and follow up people few years, write a paper, and then double the dosage, follow people few years, write a paper, double the dosage, and so on. And then it's very slow progress of learning what would be the good dosage. And we know that then eventually the kind of the benefit, for if it would be something like for migraine, these very strong headaches, that higher dosage would help. Eventually, beyond some point, it doesn't help anymore. Additional effect, if you don't get migraine headaches anymore, increasing dosage doesn't help. But at the same time, there's possibility that at some dosage, you start to get also some side effects. And the amount of those side effects also increases. And then you would want to find dosage which would, or maybe here, depending on how these curves are, maybe here, that you get at least part of the headache away, not much side effects. And then, of course, depending on the patient, at what kind of side effects there might be patient variation also, how strong the side effects are. But it's possible to do this kind of online, that start with the small dosage, but already during that first study, start to give higher and higher dosages when seeing that these lower dosages doesn't cause too many side effects. But also, as soon as we start to see side effects, then collect more information somewhere in the safe region, and then more kind of slowly try to look where we can be that we don't get too many patients with bad side effects. This is also called Bayesian optimization, and it got very popular a few years ago in machine learning, deep learning, optimizing model structures, regularization parameters, learning algorithm parameters. In machine learning also these regularization learning algorithm parameters, sometimes called hyperparameters, which is different what's in Bayesian models. It's getting more and more popular in material science. This is something which has been used for optimizing like car engines. I did tell about drug testing, and also these kind of ideas are used in Bayesian inference for stochastic simulators, like likelihood-free inference, what Ian and the Samuel Kaski have been also doing, and there's this Elfi software using these kind of ideas. And so there's a lot of these things, and it kind of this is the part which is probably the most widely used case of using Bayesian analysis, because there's something that can be done repeatedly, and they are more clear utilities and cost functions. These mobile game companies are optimizing the games so that how they can get people hooked to games and get more money out of them, and so on. Here's an example illustration of Bayesian optimization of some continuous function. It could be now, for example, these kind of what would be the best parameters for some machine learning algorithm. So I don't show you currently what is the true function. So it is also now unknown for you, that function. In the upper plot, the circle in the middle is one observation of that function. And so we know that, okay, that function gets that value there. We fitted nonlinear Gaussian process model there. And the black line in the upper figure then says that, okay, knowing just this one observation, maybe the function is flat, and then the dashed lines tell maybe it's not flat, and this is our uncertainty where the function might go. This acquisition function is now that way that lower value tells we would like to get new observations where this has a low value. So we don't want to get new observation very near where we already know the function value. We would like to know it somewhere where we have a lot of uncertainty. Maybe we can find the minimum of function somewhere over there. So we are currently trying to minimize some unknown function. We get another observation over there. We have still a lot of uncertainty, but we don't want to get the new observation here or here soon. But now it seems that maybe we should get additional observation from there. And then we're good to get observation from there. And now, in addition of reducing the uncertainty, at some point we also start to get this situation that it's more likely that the minimum of that unknown function is probably somewhere here. We have still some uncertainty that, okay, maybe the minimum is also here. But since we have observed much lower value of function here, it's very unlikely that the minimum would be here, assuming, again, certain smoothness assumptions for the function. And now, the Bayesian optimization, it's in addition of kind of the taking care of where there's uncertainty, but it also wants to get more function evaluations where it's more likely that we've actually found the minimum. So there's some balance between kind of the exploitation, get more observations where you are likely to find the minimum, and then some exploration, check also regions where there's a lot of uncertainty. And for example, in this case now, it's quite certain that additional observations there are not going to help find smaller values of the function, but there's so much uncertainty that we need to check also over there. And then we start to be quite certain that the minimum of the function is over there. And now the red line in the top plot is showing the true function. In this case, true function actually kind of quite well fulfills the smoothness assumptions. And then that's why it is also that this smooth Gaussian process was able to predict quite well how the function looks like between the observations.
Excuse me, how did you get the acquisition function?
So there are different acquisition functions. So this specific acquisition function was kind of making the balance between what is the probability that you could find. So the acquisition function, what is the probability that you could find somewhere in this point function value which is smaller than any of the previous values. And then of course you can get high probability for that either because you are already predicting that you are having that the nearby they are very low values, or because you have so much uncertainty. And there are different of these acquisition functions which have a kind of different balances between this exploitation, look more where you already have seen small values, or look more where you have a lot of uncertainty. And they are also these different acquisition functions are partially connected, that you can get similar behavior by tuning the balance between these exploitation and exploration. And these are this Bayesian optimization. So all these big companies, Google, Facebook, Amazon, Apple are using them for optimizing these machine learning systems, but also optimizing many other things like how to get more money out of customers, or how to optimize some there's the like you could also have this kind of online optimization of where for the delivery routes that can take into account uncertainties also in traffic, but also in a way like Amazon is also predicting that who is likely to order something and they need a delivery certain day, and very complex things can be optimized with these approaches. I previously talked about model selection, and that is also a decision problem, action, which model to choose and use, and then expected utility of using the model in the future is part of that. Questions?